All right, so fill in as we go along here. You guys want one?
Yeah.
What? Oh, I thought you guys were on. All right, so Oersted, I don't know how to say his name, but anyways, he discovered that a current running through a conducting wire will produce or induce a magnetic field around the wire. Where's the one for? Okay, so this is kind of key. So to determine the direction that the magnetic field is going around the wire, compasses were placed in various locations around the wire, and the north end of the compass needle was observed to determine that magnetic field. So we use the symbol, the dot, to represent anything coming like out of the page. So if we're kind of trying to draw this to represent which way things are going, it's kind of difficult on paper. So there's kind of these things where the dot means it's like coming this way, and the X means it's going in. Okay, and I'll kind of explain as we go through. But so if I was to like have a wire and I looked in on it like this, okay, so it's like a cross section. Okay, so if this is my wire and I'm looking down on it, here's the X. So this is representing that if I look down on this wire, the electrons are running into it. Okay? So when we have a current like that, okay, and let's actually just write this equals current running into the page. Okay? And this is representing a cross section of conducting wire. Okay. So say that there's this current, and around it compasses are placed. So say if I put a compass right there, okay, if I put a compass right there, the north end is going to point that way. Okay. If I say put the compass right here, it's going to go this way. If I put it right there, the compass is going to be pointing in those directions. Because the magnetic field is going like circular around it. Okay? Because that current is inducing a magnetic field around the wire. Pardon? Oh, okay. I'll get to that next. That's the next thing. So, good question. Okay.
What would the compass look like if you drew a compass instead of an arrow?
Like if you have say your compass here, okay, it would be that the arrow of the compass is pointing that way.
Like there, that's normally pointing
It's not pointing toward like Earth's geographic north. Magnetic north. It's pointing in the direction of the magnetic field that's being induced. That's why it keeps changing. Yeah. Because it's almost like it's going in a circle around the wire. The magnetic field goes around. Okay? So if we were to kind of represent this, kind of sketch it, it would be, we could do this. There's our wire. And so we would draw the magnetic field. It's like a circle around. And in this case, it's going in this direction. Okay? Now, it is going in this direction based on the direction of the actual current of the electrons. So if the electrons are flowing in this way, then, okay, so if my electrons are flowing this way, so that's my thumb, they're going in, then my fingers show which way the magnetic field is going, because it goes around it. So I'll do this. This is the rule. Okay. So the first left-hand rule, because there's multiple left-hand rules. So the first left-hand rule. Oh, I should have wrote it here too. This is the induced magnetic field. Okay. So the first left-hand rule is a general rule developed to determine the direction of the induced magnetic field lines produced around a conducting wire. Produced around a conducting wire. Based off the direction of the current moving through the conducting wire. So based off the current. Okay. So here, so if we looked at this diagram here, the fingers here are showing the direction of induced magnetic field. Okay, and then here where we have this arrow, going this way, that is the that's the flow of the electrons, and so that's what our thumb is showing. Okay, is that it's going that way. I shouldn't draw two arrows. Okay. Okay, so the thumb, so you can do it with me, the thumb points in the direction of the electrons, and the hands point in the direction of the induced magnetic field, so it's like going around this way. Okay.
Does it always give you the electric current?
Or it would give you the magnetic field, and you have to determine the electric current. Yeah, either one. So then, so then for this example, so say it was told that you have the electric current and it's going this way, so then you put your thumb up, okay, and then you see, okay, look, I have my arrows are going this way, the magnetic field is going to loop around it. So the way I try and think about it almost is that my fingers kind of can go around my thumb. That's kind of how I try and visualize it. So the other way, okay, is, yeah, so we have that, and then this. Okay, so say in this one, it said the electrons were going the other way, okay? So then you would have your thumb going this way, and now my magnetic field is going in the opposite direction. All right, so the thumb of the left hand points in the direction of the electron flow, okay? Fingers will circle or wrap around the wire in the same direction as the magnetic field lines. The left hand rule only works for the flow of electrons or negative charges. So you use the right hand if you're told that there's positive flow, okay? We don't really do that very much. We're not really concerned about positive flow, but if you came across a question that said conventional current and positive flow, you use your right. Okay. You need to know one direction first, as Lisa pointed out. Either you will know the current or the induced magnetic field, and you use the rule to find the other. Okay. So, but you'll be, if you're expected to know one, you will have to know the other.